You press the plastic button. Nothing happens. You reach into your pocket, drop a quarter down the slot, and the machine clunks to life. How does this metal box actually know what to do next? There is no human sitting inside deciding to accept your money or drop a candy bar. Inside that casing, there are no physical gears turning to make choices, and certainly no mechanical brain. Everything that happens is determined by a single physical reality. Electricity is either flowing or it is not flowing, a 1 or a 0. That illusion of intelligence you experience when the candy drops is simply thousands of microscopic electrical switches reacting to high and low voltages. Engineers call the first part of this system combinational logic. This is the machine's way of making a decision right now, based strictly on what is happening in this exact second. These diagrams show the building blocks of those immediate decisions, known as logic gates. Look at the and, or, and not gates here. Imagine the coin sorter inside our vending machine. An and gate might check two conditions. Is the coin heavy enough? And is it the right size? If both conditions are met, the output is a 1. If either is missing, it outputs a 0. By wiring a few of these simple electrical gates together, the machine can react instantly to a complex physical event. It can seamlessly route a real quarter into the cash vault or spit a lightweight plastic token right back out. These combinational circuits operate incredibly fast, but they have a major limitation. They have no concept of time. The output relies entirely and exclusively on the physical inputs pressing against them right now. Think about trying to buy a candy bar that costs $1. You insert 1 quarter. The machine can't just react in that split second and then forget you paid. It has to keep a running total of your partial payment. This diagram illustrates sequential logic. Look at the NAND and NOR latches on the left. Notice how the wires cross over and feed back into each other. This physical loop traps an electrical signal, forming a memory register. Registers act like digital sticky notes. They hold on to information, bridging the gap between an action you took in the past and a decision the machine needs to make in the future. Trapping these signals creates a new challenge. Electricity moves at incredible speeds. How do we prevent the machine from counting your quarter 20 times before it even hits the bottom of the tray? We introduce a system clock. This pulsing square wave diagram shows how a digital heartbeat works. Notice how the vertical lines strike precisely on the up beat. That strike dictates the exact millisecond the machine is allowed to read inputs and update its sticky notes. The clock is the invisible conductor of the circuit. It takes a chaotic jumble of electrical signals and organizes them into a safe, reliable, step-by-step process. With our logic and memory working, how does a machine that only knows ones and zeros handle an abstract concept? For example, if you cancel a transaction, the machine owes you money. How does it represent a negative number? This graphic shows a clever workaround called signed magnitude representation. Engineers take a row of bits and assign the very first spot, the sign bit, to act purely as a plus or minus sign. The remaining spaces hold the actual amount of money. As we add more rules to handle refunds, exact change, and sold-out items, the physical machine becomes complicated. Implementing hundreds of logic rules would normally require a massive, expensive tangle of physical wires. To clean up that wiring, engineers look to this grid, known as a K-map. By plotting the ones and zeros into overlapping cells, they can treat the logic like a visual puzzle, folding redundant rules together to eliminate unnecessary components. Concepts like sign bits and K-maps are simply architectural tricks. They allow us to translate complex human math into physical blueprints that make the final machine cheaper to build and highly efficient. When we combine our present-moment combinational logic with our sticky note sequential memory, we arrive at the ultimate design concept, the finite state machine. This image shows the brain of a finite state machine. Circles represent distinct states the machine can exist in, and arrows are the strict rules for moving between them. The logic starts in waiting, then follows an arrow to counting, and finally to dispensing. The finite state machine is the master blueprint. It proves that complex behavior is achieved simply by moving between a few basic states based on fixed rules. If we pull back from the mechanical coin slots of a vending machine and dive down into the glowing pathways of a modern computer microchip, we find the exact same architecture at work. The smartphone in your hand and the server streaming this video operate on the exact same principles. Instead of 4 states, they navigate billions. All of the digital magic we rely on daily comes down to this simple foundation: logic gates making decisions right now, registers remembering what just happened, and a clock keeping the beat.